Recently, I came across a video illustrating a simple math brain teaser, which goes like this. The number 1.005, or 1 plus 1 over 200, is raised to the power of 200. In other words, it's multiplied by itself 200 times. We then compare this number to 2, and the goal is to decide which is greater. And all of this is supposed to be done, solved by hand. What's so intriguing about this question to me is not necessarily the method of solving it, although the original video is linked below if you're curious. What made me interested was this. Skipping over the work required to reach the answer, we learned that 1.005 to the power of 200 is approximately 2.712. Some of you may recognize that this number is suspiciously close to the natural exponent, e, so keep that in the back of your mind. If we then take this equation and generalize it, we get something like this, where the fraction and exponents are inverses. In other words, the fraction that we add to 1 is 1 over the value of the exponent. We can graph this as a function of x, and something fascinating happens. Now we can see that our hypothesis about the connection to e is not a coincidence. In fact, this equation is a way of defining the natural exponent. To be more accurate, though, e is defined as the limit of this function as n, or in our case, x, approaches infinity. This means that for larger and larger values of x, the equation gives us increasingly accurate approximations of e. That's why the brain teaser's answer was close, but not exactly equal to it. An x value of 200 is a pretty good approximation of e, but not large enough to be incredibly accurate. For those of you who have an understanding of the natural exponent already, you may remember that it represents continuous compounding. This can be contrasted by the type of compounding that happens in, say, a savings account, in which a certain annual percent growth rate, or APY, will be compounded and added to your account monthly. This means that with an annual growth rate of 5% compounded monthly, you can earn interest on the interest that you've earned in previous months, because that interest is part of the new starting balance every month. This bumps up the actual growth rate very slightly. Of course, instead of 5% annually, this really means that you're earning 1/12 of that every month. Now let's take this to its extreme. Earning an infinitely small percentage every infinitely small period of time. Assuming that your bank is able to calculate and distribute all the millionths of cents in our continuous savings account, this would be enough to increase our total interest earned in a way that's directly related to E. Now, without taking too long, I'd like to compare this to a very common mathematical issue, comparing infinities. While accumulating infinitely small interest rates with infinite regularity might seem like it would yield either no growth or infinite unbounded growth, these two extremes are able to find a sort of compromise that we can express as a real number. This concept pops up very notably in calculus, when we need to integrate or accumulate the area underneath a curve with perfect accuracy. To do this, we have to take an infinite number of infinitely small slices of the function and add them all together. This might seem like an infinite problem, right? And yet we can, in many cases, find the exact answer to that infinite sum. To me, this is a characteristic of math that's so incredibly confusing, yet elegant and important. If you'd like a much more in-depth explanation of the natural exponent, I recommend this video. The creators have a uniquely brilliant way of explaining the concept, and I really gained a lot of intuition about how, at its core, E represents a very natural growth rate. I'm glad I took the time to watch it.